Hello and welcome to this course in quantum field theory. Today we're going to derive Euler-Lagrange equations for a scalar field phi. So let's begin with action S, which equals integral of Lagrangian density, which is a function of field phi, its space-time derivatives, del mu phi, and we're going to assume an explicit dependence on x mu because we assume that our field phi interacts with some external source. So we start with varying s and set it equal to 0. This is what principle of least action states, and we're left with Euler-Lagrange equations. So we begin by transforming x mu and field phi of x. We transform x mu to x mu prime, which equals x mu plus infinitesimal variation in x mu. Similarly, we transform phi of x to phi prime of x, which equals phi of x plus infinitesimal variation in phi of x. So we write our delta S. So our delta S would be S prime minus S, and S prime would be integral of Lagrangian density, which would be a function of phi prime defined by this equation, del mu phi prime comma x prime mu, and d4 x prime minus integral Lagrangian phi del mu phi x mu d4x. So we're going to find this Jacobian that connects d4x prime and d4x. Jacobian of x prime by x, d4x. So this Jacobian connects this d4x prime and d4x. So the Jacobian is for the transformation x goes to x prime. So we need to compute this Jacobian. This Jacobian would be determinant of the derivative of this transformation with respect to x lambda. So we need to compute this derivative first. So this derivative is simply Kronecker delta mu lambda plus del lambda delta x mu. So computing the determinant of delta mu lambda plus del lambda delta x mu, we get by using a formula. So by using a formula, using determinant of identity matrix plus some small matrix epsilon, so this is approximately equal to, so this approximates to 1 plus trace of this small matrix epsilon. So using this formula, we get Jacobian of x prime by x equals 1 plus trace of del lambda delta x mu, which equals 1 plus del mu del x mu. So this term comes because we add the diagonal elements of this matrix and using the Einstein summation convention. So we get this term easily. Now substituting this Jacobian, we get, so substituting this Jacobian in this equation, d4x prime is equal to Jacobian times d4x. So substituting the Jacobian, we get d4x plus del mu del x mu d4x. So d4x prime is related to d4x by this equation. So substituting this d4x prime into our variation in action, that is here, we get delta S is equal to integration of Lagrangian of phi prime del mu phi prime x prime mu d4x plus integration of Lagrangian phi prime del mu phi prime x prime mu del mu delta x mu d4x minus integral of Lagrangian of phi del mu phi x mu d4x. Now Taylor expanding this first and second term, we get del s equal to integration of Lagrangian density of phi del mu phi x mu plus del L by del phi plus del L by del mu phi plus del L by del x mu d4x plus integral of Lagrangian density of phi del mu phi comma x mu del mu of del x mu plus del L by del phi delta phi del mu delta x mu plus del L by del mu phi delta of del mu phi del mu delta x mu plus del L by del x mu del mu of del x mu d4x minus integration of Lagrangian density of phi del mu phi and x mu d4x. Now neglecting the higher order variations, which are this term is a higher order variation, this term is a higher order variation, and this term is a higher order variation. So we are left with first of all we define delta L is equivalent to del L by del phi plus del L by del mu phi plus del L by del x mu. So our del L is this. So these three terms are our del L. Then we are left with delta S is equal to integration of Lagrangian of field phi del mu phi x mu plus delta L d4x plus integration of Lagrangian of phi del mu phi x mu del mu of del x mu d4x minus integral of Lagrangian of phi del mu phi comma x mu d4x. So first term in this bracket, that is this Lagrangian, cancels with this Lagrangian, and we are left with delta S equals integration of delta L plus L del mu del x mu d4x Now, if we rewrite this expression with the full form of del L, then we get delta S equals, so this integration is over region R, and our variations del phi equals del x mu, they vanish on this boundary of region R. So you need to keep that in mind, that our variations vanish on the boundary of R, and this integration is over this region R. And so first of all we have del L by del phi plus del L by del mu phi del mu phi plus del L by del x mu. So this is our del L. Then there was L del mu del x mu d4x. So this is our del S. Now we can show that del and del mu commute from this equation. X prime mu equals x mu plus del x mu. Phi prime of x is equal to 5x plus variation in phi. So we can use these two equations to show that del and del mu commute. So substitute this x prime here instead of x. So our x mu transformed to x prime mu. So substitute that into phi prime of x. So after substituting into phi prime of x, we can show that phi prime of x plus del x equals phi of x plus del x plus del of phi of x plus del x, and Taylor expansion of these three terms would give us phi prime of x plus del mu phi prime of x delta x mu is equal into phi of x plus del mu of phi of x delta x mu plus delta of phi of x plus delta of del mu phi of x delta x mu. Then we can write this phi prime of x and this phi prime of x as delta phi and that delta phi will go away plus del mu phi prime of x delta x mu is equivalent to phi of x plus del mu phi delta x mu plus delta phi. So this delta phi would go with this delta phi plus delta del mu phi delta x mu. So we can write, instead of these two terms, we can write del mu delta phi delta x mu is equivalent to phi of x. Oh, sorry, this phi of x was gone. So we can write is equivalent to del mu phi del x mu. So which implies del mu del phi equals del of del mu phi. So which implies del and del mu commute. So we can use this property here. We can use this property here and exchange the places of those del and del mu. So we get, let me copy this and paste it here. So after exchanging, we get del s equals integral over region R del L by del phi delta phi plus del L by del mu phi del mu del phi plus del L by, oh, we can rewrite these two terms into a single term, that is del mu of L delta x mu, because by using product rule we get these two terms back. So integration is with respect to coordinates x mu. So we can rewrite this term as del mu of del L by del mu phi delta phi minus del mu del L by del mu phi delta phi. Now you can compute the derivatives here and you will get this second term back. Now substituting these into del s, we get integration over R del L by del phi minus del mu del L by del mu phi del phi d4x plus, so we change one integral to surface integral, so integration is over the boundary of R del L by del mu phi del phi plus Lagrangian times del x mu d sigma mu. Now we know that our variations vanish at boundaries. So delta phi equals delta x mu equals 0 on our boundary. So our integral over the boundary vanishes. So we're left with one integral, and since delta phi is arbitrary, which implies del L by del phi minus del by del x mu of del L by del mu phi is equal to 0, which is our Euler-Lagrange equation for scalar field phi. This is our Euler-Lagrange equation. Thank you for watching.